Okay, great. So it is a great pleasure to introduce Professor Frosini that will do the last lecture for the geometry of deep learning. So this time will be a lecture on topological data analysis. So not really like, it's a bit different than what we did the other times, but I figured that I wanted to give you guys a little bit of flavor, all the flavors of the geometry and machine learning, right? That's the idea. What geometry can do for machine learning. So this is it. So please, Patrizio, come and
Okay.
everybody.
Thank you so much. Let me check if
Yes. So
is the camera working properly. Maybe you change the.
Okay, I show you. So the thing is that if you start making noise, it means that somebody, you have to authorize people, okay, if they arrive late. Sometimes people do arrive late.
Okay.
So these are the people. This is how you see yourself.
Okay, that's okay.
Okay.
I'm just managing that.
Yes.
No.
Okay. No.
Here.
Yes.
Okay.
Perfect.
Okay. So good afternoon. I'm going to speak about a view of geometric deep learning based on group equivalent on responsive operators. But the first slides are just a kind of narrative about this approach. So for, let me say, 10 slides, my presentation will not be about mathematics, but about pictures and some kind of epistemology, clarifying what this approach means in general terms. So I have chosen this title from analyzing data to studying observers, a journey through 4 recent papers. I have taken 4 papers of mine in order to present 4 different talks. Okay. So let's start from this outline. I will speak about the key role of observers in data analysis. Let me be a little bit provocative. In my view, no one is interested in data. No one in the world is interested in data. Everyone is interested in the reaction of observers in the presence of data. This is the general epistemology of this approach. After saying that, with some pictures, I will speak about topological and metric basics for the theory of group, equivalent, and responsive operators, Geneos. Then I will face the problem of building linear and nonlinear Geneos. And finally, I will say something about applications. So the key role of observers in data analysis. We start from this fact. Data can be often regarded as functions. But in any case, you can think also of different kind of information, but in many cases, you have to manage functions. For example, an electrocardiogram is a function from the real numbers to the real numbers. A gray level image is a function from the real plane to the real numbers. Or if you prefer, a function to the set of integer numbers between 0 and 255, okay? Or something like this. A computerized tomography scan is a function from a helix to real numbers, where there is a body and there is a helix going around the body. In reality, we have a body moving through a ring, but this is equivalent to consider an helix going around a body. For each point of the helix, we have an X-ray beam going through the body, and the machine records the quantity of mass encountered by this X-ray beam. So for each point in the helix, we have a number. It is the quantity of mass. Maybe you could say, but not every kind of data is of this kind. It is true, but please consider this fact. Imagine of a cloud of points. You can say it is not a function, but it is equivalent to a function. You can consider this cloud of points in R3, and you can consider the function measuring for each point in R3 the distance from the cloud of points. Of course, the cloud of points is the set of 0 points for the distance. Each point in the cloud is a point with a distance equal to 0. Okay, so if you give a function, you have a cloud. If you take the cloud, you have a function. So a cloud point in Rn is equivalent to a real valued function. If you take a graph, of course, a graph is not considered a function, but even in this case, we have a function. You can consider the, are you saying that the voice were not, okay. So.
Excuse me, sorry to interrupt you.
Can you say?
You haven't shared your screen. We cannot see online the slides.
Oh, so I have to share the screen, and how can I?
Thank you.
Thank you. So let me. Okay. Yes. Okay, so this is.
Now we can go back to Adobe.
Yes, then you can.
Is that okay? Can you see my screen now? Can you see as?
Yes, thank you.
Yes.
Okay. Sorry for that. I apologize. So this is just the slide saying that functions are quite frequent as data in applications. But when we consider a graph, what is a graph? A graph is an adjacency matrix that is a function from the cells of a matrix to the set 0, 1, or to an interval if you wish to have weighted graphs. So in many cases, you can reduce your information to a function, okay? Now, I do not understand if you can see the whole screen or just part of the screen, since do you think that black bar is covering anything? Can you see the whole image, or I do not know if the title is covered? Or...
Yes, a moment. So we try to put it, I don't know where
maybe
okay,
we
like
can...
that.
Okay.
This is the best possible.
I guess, okay. Okay, so data are processed by observers. Data have no meaning if no observer elaborates them. We cannot speak about data without an observer. At least this is let me say, the model we are considering. An observer is an agent that transforms data according to some rule, frequently according to some kind of symmetry. And this is quite important. When you say that we are just considering some, let me say, measuring of reality without an observer, it means that there is some observer that is hidden in the model. For example, we can say that measuring this table does not require any observer. In that case, we are saying that any observer is equivalent in some sense. There is an observer, but any observer you can choose is the same in some sense, since the procedure is similar for any possible observer. We need to have observers. Now, observers are variables in data analysis. When we change the observer, we change data interpretation. And data interpretation strongly depends on the chosen observer. Okay, this is just a cartoon, but it's clear in saying that if you change the point of view, if you change the observer, in general terms, you completely change the analysis and the judgment concerning the data. Our interest in data is greatly overrated. It's important to understand that we are hardly ever interested directly in data, but in the reaction of the observer to the presence of data. I have thought about what could be a symbol of this approach, and I have chosen this famous joke by Groucho Marx, saying, from the moment I picked up your book until I put it down, I was convulsed with laughter. Someday I intend reading it. The important part is not the book, but the reaction. Obviously, of course, this is just a joke, but it's true in the sense that data does not matter. What matters is the reaction of an observer or a family of observers to data. Data structure. We often say that data brings structure. In this approach, it's clear that data never brings structure. Every structure is something that is written in our model, in our approach to reality. For example, when we cannot, in my view, in the view concerning geometric, this kind of geometric deep learning, when you speak about, for example, a manifold or a Riemannian manifold or some different kind of structure, you are thinking of something that is written in the model that is in the observer, and it is applied, this model is applied to reality. So the inner product is here, and we are projecting this inner product to reality. Okay? Generally speaking, there is no structure in data. The structure of data is a projection of the structure of the observer. When you change the observer, similar data change their meaning completely. Another important point in this approach is that observers are often associated with invariance groups. Observers often think that some data are equivalent to each other according to an invariance group, but this invariance group is a variable in the problem. For example, this is just a trivial example. If you are interested in comparing shells, it is quite natural to consider the group of isometries of the real plane. We have an image, and we can move this image of a shell around in the plane, and we can say that these two shapes are equivalent to each other, since I can rotate when I use the group of isometries. But if I say that I'm interested in letters, I have to change the group, since I cannot rotate an M letter and change it into a W letter, okay? So it's important to recognize that invariance groups are fundamental, but they are just a variable in the problem. Representing observers as equivariant operators is the purpose of this talk. I'd like to propose you a way of representing observers as operators that change functions into different kind of functions. I have to say that we can consider observers as structures able to change data into other data, and we have to recognize that usually they respect some data equivalencies by computing with some transformations. As a first approximation, observers can be represented as group equivalent operators, GEOs. But in this talk, I'm not going to speak about GEOs, group equivalent operators, but about Geneos, group equivalent non-expansive operators. Let me say something more about this. So I'm going to explain this in detail later, but an equivalent operator is an operator that commutes with the action of subgroup. For example, I can consider a convolution of an image with respect to a symmetric kernel. Okay, I can blur an image by means of a symmetric kernel, and then I can move the image. Or I can move the image, and then I can blur the image. And the result is the same if the kernel is symmetric. So this is a kind of geo, a group equivalent operators. Or you could think about an operator that change each function into just a number, the maximum of the function. And these kind of things. Of course, if you, in this case, we will see, but it's quite natural, and you already know about this. If I move the image and then I compute the maximum, it's the same then computing the maximum and then taking the trivial transformation given by the trivial group. So this is just an invariant operator, a particular case of equivariant operator. But let's skip this point. I'm going to give you other examples later. Why non-expansive? Why not just equivariant operator? There are two reasons, two important reasons indeed. First of all, observers are often assumed to simplify the metric structure of data in order to produce meaningful interpretation. You can complexify data in some sense, but this is not so useful. You can do that for some time, but at the end, you have to simplify your data. You have to understand if your image contains a dog or not, 0 or 1. At the beginning, you can change the data in the sense of augmenting the information, but at some step, you have to go down to a simplification of information. So this is quite important in data analysis and also in geometric deep learning. You have to simplify at some stage the information you are managing. Secondly, this is more technical, non-expansiveness guarantees good topological properties. And this is also important. Basically, it guarantees compactness of the space, but we will see this later. So this is the presentation. We have to take this into account. The message is data are not so important. Everyone says that data are important from any point of view. We have to study data, we have to change data, we have to multiply data and so on. But in this approach, you say data are not important. What is important is the observer, the reaction of the observer to the data. Okay, for example, I take a picture, I have a lesion skin here. Okay, what is important? Is the picture of this skin lesion important? No, I'm not interested in that. I am interested in the reaction of my physician, the reaction of the physician to the image. If the physician says, don't worry, Patrizio, about that, this is what is important to me. Okay, if I give you my cell phone number, I'm not giving you, let me say, a prime number or a different kind of number. I'm giving you a mean to contact me. What is important is the reaction that you can consider with respect to this number, and so on. So what we are interested in is considering not the approximation and the study of data, but the approximation and the study of the space of observers. We have to move in the space of observers. We are interested in the topology of the space. We are interested in the Riemannian structure of the space of observers. We are interested in the curvature of the space of observers. Is that clear? This is the general view. How can we do that? How can we respect these principles? Okay, I'm going to present to you four recent papers about the research concerning Geneos, group equivariant non-expansive operator. The first paper is towards a topological geometrical theory of group equivariant non-expansive operators for data analysis and machine learning that appears 3 years ago in Nature Machine Intelligence. In this paper, we proposed this view of operators in order to approximate observers. Let me read the abstract in order to present this. At the end, these slides will be available. And so you will be able to click here and to see the paper, okay, and the result you are interested in. Of course, there is, I cannot say a lot of mathematics, but there is mathematics. I cannot explain the details, okay? So I have to go back here. Okay. In this paper, we provide a general mathematical framework for group and set equivalence in machine learning. Equivalence with respect to groups, but also in some view with respect to sets, since you know that it is important that you cannot apply, I will speak about groups. But if I take a horse and I compress this way once, twice, and so on, at the end, I have a segment. And I cannot say that this is still a horse. I can say that in some sense, but it is not acceptable. So when you iterate, when you consider the group, we are doing something dangerous. But anyway, now we are speaking about groups, okay? We define group equivalent on expansive operators, Geneos, as maps between function spaces associated with groups of transformations. We study the topological and metric properties of a space of Geneos to evaluate their approximating power and set the basis for general strategies to initialize and compose operators. We define suitable pseudometrics for the function spaces, the equivalence group, and the set of non-expansive operators. We prove that under suitable assumptions, the space of Geneos is compact and convex, and blah, blah, blah. Okay, now some mathematical details. I'll start with mathematics now. Let X be a non-empty set. Think about, for example, the set of points on the plane. You are interested in images, and so you consider the points on the plane. X is the set of points. Or, for example, the points of a real line if you are interested in electrocardiograms, and so on. You have just a set, not a topological space. But now you have some measuring tool. You can measure something. For example, you can take a picture. Okay? Let phi be a topological subspace of a set of all bounded functions phi from X to real numbers, endowed with the max norm distance. Okay, so I use this symbol, d phi, in order to say I'm considering the max norm distance between images. For example, we can see X as the space where we can make our measurements, and phi as the space of all possible measurements. We will say that phi is the set of admissible functions or admissible signals. In other words, phi is the set of all functions from X to R that can be produced by our measuring instruments, tools, or by other observers that give us this data. For example, a gray level image can be represented as a function from real plane to the interval 0, 1. In this case, X is the real plane. Pay attention. It is not true. Sometimes this space is a vector space, sometimes. But it could be a different thing. For example, if I take an image and I multiply as a function from real plane to 0, 1, and I multiply by 2, this is no more an image, since the value is beyond the white. Okay, I cannot take 2 is not a color when we normalize the values. Okay, or think about an electrocardiogram. You cannot multiply this by 1 million. It is no more an electrocardiogram. So you can have, in some lucky case, a vector space, but maybe not. Let us consider a group G of bijections from X to X. I consider permutations of a domain such that we have this property. If you take a function that is legitimate, that is admissible, and you combine phi with G, you obtain another admissible signal. Think about the picture of a cat. You cannot consider a permutation that rotates the image, but you cannot take a general permutation. If you do that, you get just noise, an image that has no meaning. You cannot permute each point of the image. I guess that this is clear. So you have to decide which kind of permutation you can consider, and G is a variable. When you have this, a set of functions and a group acting on this set of functions by composition, you have a perception pair, what we call a perception pair. The choice of a perception pair states which data can be considered as legitimate measurements, the functions in phi, and which group represents the equivalence between data, the group G. To proceed, we need to introduce suitable topologies on X and the group. Before doing that, we recall that the initial topology, tau in on X, with respect to phi, is the course's topology on X, such that every function phi in phi is continuous. I do not know if this is clear to you. You have a set of functions. X is not a topological space. There is no meaning in saying, in wondering if these functions are continuous, since you haven't a topology. So the statement, these functions are continuous, has no meaning at all. But you can endow X with initial topology, that is the course's topology, such that any data, any admissible function is continuous. Okay, now we consider, and this is the initial topology tau in. Now we consider this pseudometric on X. What is pseudometric? A pseudometric is a metric without the assumption then that when you have 0, the 2 points must coincide. So you can have different points with a distance that vanishes. Okay, pseudometric. We define on X this pseudometric. What is the distance between 2 points x1 and x2? You have your measurements. Sorry, your measurements. Okay, and you consider your measurements at your points. If your measurements reveal some difference, you can say the points are different. If not, there is no way of understanding that the points are different. Think about two objects. They have the same position, the same color, the same size, the same and so on. At the end, you have to say, I cannot distinguish these objects. In some sense, they are the same. And this is the same philosophy. The important thing is that the topology induced by this distance is finer than the initial topology. And when phi is totally bounded, coincides with the initial topology. So if you use this pseudometric, you are saying that by definition, your data are continuous. So you can have a jump in your data. And from the Euclidean point of view, you could say this function is not continuous, there is a jump. But with respect to this topology, this function is continuous. So each function, each data is continuous because of a choice of our topology, which is induced by this pseudometric. The use of dx, this pseudometric, implies that we can distinguish 2 points only if a measurement exists, taking those points to different values. The following properties are of use in our model. Theorem, every function, this is quite trivial, every function in phi is non-expansive with respect to a pseudometric, and hence continuous. Theorem, if phi is compact and x is complete, then x is compact. So the structure of a domain is inherited from the structure of the measurements. At the beginning, you have just measurements. There is no way of knowing reality without measurements. And there is no structure on the domain. X has no structure at all. But now you have a measuring tool. You can induce a structure on the domain by using this pseudometric. Is that clear to you? Okay, this is the philosophy. All the structure comes from your measurements. In the following, we will usually assume that phi is compact and x is complete, and hence, because of this theorem, compact too. Now, some magic happens. Each bijection is an isometry. Think about this. Let us consider the group of the bijections from x to x, and I use this symbol, bij of x. The group of bijections can permute each point in your domain, okay? And we can consider, we can consider bij phi of x, so it is the subgroup of a previous group of each permutation, such that when you compose this a function, a legitimate function, an admissible function with this permutation, you get another admissible function. And this is true also for the inverse of our permutation. Okay, so you have a restriction. You have bijections and the set of phi preserving permutations. The permutations that preserves data. In the previous example, when I spoke about the cat, it is not allowed that you permute each point without any criterion. Okay, we can do the same for the group of homeomorphisms of X. We have a pseudometric, so we have a topology in X. So we have bicontinuous maps, homeomorphisms, bicontinuous maps. Functions that are continuous with inverse that is still continuous. And we can consider the subgroup of the phi preserving homeomorphisms. Okay? And we can do the same for the isometries. We have a pseudometric, so we can consider the bijections that preserve the pseudometric, the pseudo distance. And this is iso of X. And we have a subgroup of the phi preserving isometries. What happens? It happens that these three groups coincide. And what is the reason? The reason is that we have chosen a pseudometric in order to get this. Each bijection, since it must preserve the data, is an isometry. This is quite an important point. Now, let us now focus our attention on a subgroup G of homeo phi of X, phi preserving homeomorphism. We can define this pseudometric. You can imagine this alone, since what is the definition? What is the distance between two permutations, G1 and G2? You have some test function, you have the admissible signal, and you compose each admissible signal phi with our permutation, G1 and G2. If you can see the difference between the functions after the composition, you say the permutations are different. Sometimes you cannot do that. Imagine that you have just constant functions on the real plane. Now you permute points, and you cannot see the difference. Each function, constant function phi, composed with any permutation is equal to phi composed with any other permutation, since the function is constant. So the pseudo distance between two permutations in the case of constant functions is 0. Is that clear to you? When you change the set of data, you are changing the way of measuring the distance between points, the points in X, and you are changing the way you measure the distance between homomorphisms. Everything comes from measurements. This is the important point. Think about this. Theorem: G is a topological group with respect to this pseudometric, and the action of G on phi by right composition is continuous. I do not know if everyone knows about the definition of topological group. Anyway, let me repeat. It is just a group where the operations are continuous. Okay, this is a topological group. Theorem: if phi is compact and G is complete, then G is compact. It is quite analogous to the other theorem. If phi is compact and X is complete, then X is compact. Okay. Geos and Geneos. Now, formally, I can introduce group equivalent operators and group equivalent non-expansive operators. Let us take a perception pair. It is a pair phi G, phi a set of admissible data, and G a group acting by right composition on this set, under the assumption that G is made of phi preserving homomorphisms. But I could say phi preserving isometries or phi preserving bijections is the same. I take this perception pair, and now, okay, I can also take two perception pair of this kind, phi G and psi H. Let us consider a homomorphism T from G to H. Okay, a way of interpreting the transformation in on phi as transformation on psi. Okay, a homomorphism. Each function f from phi to psi, such that we have this equality. So we have a commuting diagram. Okay, you can apply, we can compose with G and then you apply F, or you can apply F and then you compose with the not G, since you are in another space, T of G. This is equivalence. Everyone working in neural networks knows about this. Okay, equivalence. This is a group equivalent operator, a GEO. If you have also non-expansivity, that means the distance between the images f of phi1 and f of phi2, I mean a distance with respect to the max norm, is less than or equal to the distance of the original data, phi1 and phi2. In this case, we say that f is called a group equivalent or expansive operator associated with the homomorphism T. Okay, for example, when you consider images and you consider, I told you about the blurring, if the mass of your kernel is less than 1, you have not just a geo, but a genome. What happens is that the distance between images decreases when you consider the blurring. But let me give you a simple example about Geneos. Let us assume that we are interested in the comparison of a distribution. I see that there is maybe. Okay, this is about the previous problem. Okay, let us assume that we are interested in the comparison of the distributions of temperatures on a sphere taken at 2 different times. So we are thinking about the Earth. Okay, red means hot, white means cold. Okay, we have 2 different distribution of temperature. We cannot see the countries. We can just see the North Pole and the South Pole. Okay, so we cannot say this is the USA, this is Italy, this is France. We cannot say. We can just distinguish the temperatures. And someone, okay, on the left, let me say, for example, we have the temperature today. On the right, the temperature exactly 1 year ago. What is the difference? How different is the distribution of temperature? You can say, I compute the L1 or L2 distance. This is not reasonable, since maybe the position of the Earth is different. So you have to rotate a little bit in order to match the same countries. Maybe you are matching the Sahara Desert with some different place, so you cannot compare the temperature. Okay, so there is a group, and the group is a group of rotation of the sphere. Okay, let us also assume that only 2 okay, I told you about this. Now I'd like to, okay, let us introduce 2 perception pairs, phi g and psi h, by setting. The first perception pair is like this. X is the surface of the Earth, S2, the surface. Phi is the set of 1 Lipschitz functions from this surface to a fixed interval AB, that is the interval from the minimum possible temperature on the Earth, okay? Let me say minus 60, okay? And B is the maximum possible temperature, okay? G is the group of rotations of S2 around the axis North Pole, South Pole. You can rotate your Earth, okay? So data, distribution of temperatures, and the group acting on the data. But we have also another interesting perception pair. Y is the equator, S1 of S2, the equator. Psi is the set of 1 Lipschitz functions. Remember, 1 Lipschitz means that the ratio between the distance in the image and the distance, the original distance, is less than 1. Okay? From S1 to the same interval AB. And H is the group of rotation of the equator. Now, I give you a simple example of Geneo from phi g to psi h. I have to give you a homomorphism between the groups and a map between the admissible signals. T of G is the map taking, this is quite natural. I take a rotation of alpha degree of S2, and the corresponding rotation for the equator is the rotation of the equator of alpha degree. In some sense, it is the identity, but the group acts on different spaces of data. Okay, is that clear? Okay, T just take a rotation to the equivalent rotation. F of phi is the function of psi that takes each point y belonging to the equator S1 to the average of a temperature along the meridian containing y for every distribution of temperature. So you ask me, what is the value at this point of a function f of phi? Phi is a distribution of temperature over the Earth, okay? And you ask me, what is the temperature at this point along the equator, belonging to the equator? I take the meridian going through that point. I take the average of the temperature of the global distribution along this meridian. And this is the value at that point. This is an operator transforming a distribution of temperature on the Earth to a distribution of temperature along the equator. In plain words, we can check this. I'm not going to do this. Okay, this is a Geneos. In plain words, our Geneos simplifies the data by transforming temperature distributions on the Earth into temperature distribution of the equator. Simpler data that can be managed in an easier way. A Geneos is just a machine to simplify data. It is an observer that changes data by simplifying them in some sense with respect to the action of the group. This is the meaning. To key results and to good news for applications. Let us assume that a homomorphism T from G to H has been fixed. Let us define the metric D Geneos on the set of Geneos from the pair phi G to the pair psi H by this trivial definition. What is the distance between two operators? It is just the supremum varying the admissible signal in capital phi of the max norm distance between the images f1 of phi and f2 of phi. So the distance between operators is just the distance between the way they act on the data. Okay, please pay attention. Phi is not a vector space. We are not considering a vector space. It is just a set of functions. Theorem, if phi and psi are compact, then this set of Geneos, the set of any Geneos between phi G and psi H is compact with respect to our metric. What does it mean? It means that if the set of data is compact, think about the distribution of temperature I told you. It is a compact space. One Lipschitz functions taking values in 0, 1. It is a compact space. Then you can say that the set of observers is compact too. Think about this. In real life, this never happens since we are using different pseudometrics and topologies. In real life, you can have quite simple data and quite complex observers. I look at this pen. The pen is quite simple, and I think I'm more complex than this pen. Okay, so it is quite different. The space of data is completely different from the space of observers. Sometimes we have the reverse relation. It is possible that maybe I look at the world is more complex than me. The observer is not so complex as the object that is observed. But this theorem says, pay attention, if you choose the right topologies, you can say that when the space of data is compact, the space of observers is compact too. So if you can approximate the space of data, since when you have a compact space, you can take a covering and you can extract a finite covering, and so you can approximate, you can epsilon approximate your space, then you can also approximate the space of every possible observer. This is counterintuitive, but it is counterintuitive because we are usually using different topologies. If psi is convex, then the set of Geneos is convex too. And this is important since let me make this 2 key observations. While the space of data is often non-convex, and hence averaging data does not make sense, the assumption of convexity of psi implies the convexity of the space of observers and allows us to consider the average of observers. We can take different observers, and we can compute a barycenter of observers, and this is still an observer. What is our main goal in this game? Our main goal is to develop a good geometric and compositional theory to approximate an ideal observer. In our model, approximate an observer means to look for a Geneo f that minimizes a suitable cost function, C of f, maybe a distance from the ideal observer. The cost function quantifies the error that is committed by taking the Geneo f instead of the ideal observer. Since the space of Geneos is compact and convex under the assumption that the data spaces are compact and convex, if the cost function C of f is strictly convex, we have that there is one and only one Geneo that best approximate the ideal observer. In many cases, we cannot take the whole space of Geneos, okay? So it is important that we have some general guarantee about the approximation of the ideal observer. Now, this is the time of maybe having a stop, I think. Any question about this general presentation? No, so I stop, what can I say, 10 minutes? Okay, should I stop this recording or? I do not know, I cannot see, but since
Any questions? Okay, so we start again at 4:40, okay?
Great.
Ok, grazie. Okay. Ricominci, you have to start again, I'm sorry about that.
Okay, so we have to move just in the space of a, let me say, smart observers that can be of help. This is a big difference. We are considering a geometric approach to this kind of problem. We are not considering a space, a huge space, depending on several billion of parameters, but just to consider a small space with respect to the number of parameters that represent the observers that are smart as for this problem we are focusing on. So after seeing that, we have to build this space made of just a few, let me say, the application I will show at the end, we have 17 parameters. So a space of dimension 17, okay? So small spaces of observers that are considered suitable for facing the problem we have chosen. So the second paper I'd like to consider is this paper on the construction of group equivalent and expansive operators via permutants and symmetric functions, published on Frontiers in Artificial Intelligence. And this paper is available by open access here by means of this link. Okay. I hope that there is a connection. Okay, and in this case, we have to consider, let me see if maybe, no, I have, it's better if I go back to the pictures I have prepared previously. So, okay. Okay, first of all, there are elementary methods to build Geneos. Okay, I would like to list these simple, trivial methods to build Geneos. The first method is composition. You have a Geneo from phi g to psi h. You have another Geneo from psi h to chi k, and you have the corresponding homomorphisms between the groups. So you have T1 and T2. It's quite trivial. It is a simple exercise to prove that the composition of Geneos is a Geneo with respect to the composition of homomorphisms. So composition is the most trivial way of getting new Geneos. Then you can use another simple method to get Geneos is considering using one Lipschitz functions. So let us consider n Geneos f1, fn from phi g to psi h, to perception pairs, with respect to the same homomorphism between the group G and the group H. Then let us assume that we have a one Lipschitz map L from Rn to R, and can consider the induced map L star that is defined this way. Okay, maybe I didn't, okay. I just wrote L star is the map induced by L, okay? If we consider this map and we assume that L star of phi f1 fn transform phi into psi, that means that this operator transforms the new operator, L star f1 fn transforms the set of admissible signals into the other set of admissible signals. In that case, we have that L star f1 fn is still a Geneo with respect to T. Let me give some simple example in order to make clear what the meaning of this proposition, what is the meaning of this proposition. And so I'm going to illustrate three propositions that follow from the proposition based on Lipschitz functions. Okay, Geneos are a lattice. We have a lattice of Geneos. This means that when we take F1, Fn Geneos from phi g to psi h, with respect to the same homomorphism T from G to H, then the maximum of our operators and the minimum of our operators is a Geneo, provided that this operator takes phi into psi. So when you minimize Geneos, you get a new Geneo. When you maximize Geneos, you get another Geneo. You have a lattice of Geneos. Secondly, and this is just a trivial application of a previous proposition, okay, where the one Lipschitz function is just the maximum and the minimum on the other side. Then you have translations. If you take a translation and you translate a Geneo this way, you consider F, when you have F, a Geneo F, and you translate F by considering F minus B, where B is a constant. This is quite simple. It is a new Geneo. And finally, and more interestingly, we have that the convex combination of Geneos is still a Geneo. I told you this when I claimed that the space of Geneos is convex, when we assume that psi is convex. Imagine this. Imagine that we have just three Geneos. We have a problem, we have data, we have an equivariance group, but unfortunately, we have just three Geneos. What can we do? We have a finite number of Geneos. We can consider the triangle. It is the convex combination of these three Geneos in their space. Each point in the triangle is still a Geneo, since the convex combination of Geneos is still a Geneo. So in any case, when you have at least two different Geneos, you have an infinite number of Geneos, since you have the convex combination. And this is exactly what we do in application. At the end of my presentation, I will speak about pocket detection in proteins. And we used this principle. We have just some observers that are clever, smart in some sense, and we combine them in order to get smarter and more useful operators, more useful Geneos. Okay, so these are elementary methods to build Geneos. Now I would like to present a non-trivial method to get Geneos. It is the method based on permutant measures. So in order to speak about this, I need to consider the case of a finite set, a finite domain X for our functions. Think about, for example, an image, just a finite number of pixels. Okay, so we have X here, that is X1, Xn. And then we consider the set of all functions from X to real numbers. Okay, this is a symbol I use to represent the set of functions from X to R. That is, of course, isomorphic to the Euclidean space Rn. Okay, since I just need to have n numbers for each point, for each pixel, I have a number. Okay. And let us consider a subgroup, a group of permutations of a group of any possible permutations of the points in X. So I say, okay, I have an infinite, not an infinite, I have a large number of permutations of the pixels, but I just consider translations, for example, or different kind of things, since when I consider translation, I exit the domain. Okay, I can consider, for example, a square and the rotation of 90 degrees. Okay, so I select a subgroup. What is a permutant measure? Definition: a finite signed, so it is possible to have negative values. Measure mu on the set of all permutations of the points in X is called a permutant measure with respect to our group G if every subset H of this group of permutation is measurable and mu is invariant under the conjugation action of G. So when you take a set, you choose, or you have this set of subset of permutation, you take this measure for H, and the measure for the new set, G, H, the inverse of H, the image by conjugation, okay, conjugacy. For average point G, we have another measurable set, and the measure is the same. If you have this, you say that you have a permutant measure. Is that clear to you? The meaning of the expression permutant measure? A measure that is invariant under conjugacy with respect to the action of group G. Is that weird to you or clear? I hope that it is clear. Okay? Anyway, I'm going to give you examples, concrete example, at least one concrete example of this. If you have a permutant measure, you have this proposition. If mu is a permutant measure with respect to the group G, then the map f mu from Rx to Rx, the set of functions from X to R to the set of functions from X to R, defined this way, f mu of phi is defined this way, is a linear geo, group equivalent operator. If the total mass of a measure is less than 1, then f mu is still a Geneo, a group equivalent non-expansive. What is the meaning of this? The meaning is this. You take any possible permutation in your set. There is a huge number of possible permutations. For each permutation, you have a weight, a measure, mu of H, and you consider phi composed with the inverse of the permutation. Phi composed with the inverse of the permutation is a new function defined on the set. And the weight for this function is mu of H, and you take the summation. This is a new function. This is f mu of phi. This operator is a Geneo under the assumption that the total mass is less than 1. You could say, but we cannot compute this guy since the number of permutation is huge. But in many cases, mu is almost everywhere 0. So you have to take just a small sum, just a few summands. This is an important point. So you can compute in practice this. So an example of permutant measure. Let us consider the set X of the vertices of a cube in R3. You have this cube, okay, 8 vertices. And you can consider the group G of the orientation-preserving isometries of R3 that take X, the vertices of a cube, to itself. So in practice, you are thinking of taking this cube, you rotate in such a way that the new position of the vertices is each vertex is taken to another vertex. Okay, you can do these rotations. Okay. Let pi 1, pi 2, pi 3 be the free planes, you can see them in yellow in the picture, that contain the center of mass of X and are parallel to a face of a cube. Let hi from X to X be the orthogonal symmetry with respect to pi I for each value I. So, for example, when you take pi 1, you are considering this symmetry. You have pi 1, you take this 4 points to this 4 points. Okay? This is pi 1. And the same for pi 2 and for pi 3. 3 elements, 3 permutation. And you declare, you say that your permutant measure takes these 3 permutations to a positive number C. For example, if you wish, 1/3. Okay, and every other permutation is taken to 0. Okay, so you have just 3 permutation where the value is different from 0. 3 permutation. And okay, this This is a permutant measure. This is a permutant measure. If you apply, think about this. You should try to do this. If you take this orthogonal symmetry, that is pi1, think about taking, for example, this orientation preserving isometry, this rotation. Okay, I take this symmetry and I can do that into different flavors. You can take the symmetry, or you can rotate this way, then you apply this symmetry, and then you counter rotate this. Now you get this symmetry. If you take the conjugacy action, this symmetry becomes this symmetry. So we have a permutation. This action permute the element in the set H1, H2, H3. And you can make it is an easy computation. This is a permutant measure. The measure is invariant when you apply an element in the group. Pay attention, the set H1, H2, H3 is not a group at all. It is not a group. If you compose this element, you exit the set. It is not a group, but it is stable under the conjugacy action of a group G. We will call this a permutant. The measure I have defined is called a permutant measure. This set is called a permutant. I'll say more about this later. Let me say something more about this. It is interesting to observe that the set of permutant measures, the set of functions having the properties I have stressed, is a lattice. The set of permutant measures, before I said that the set of Geneos is a lattice. Now I am saying that the set of permutant measures is a lattice. Indeed, if you take two permutant measures, U1 and U2, and you take the minimum defined this way between these two measures, you get another permutant measures and the same measure, and the same holds for the maximum. Moreover, the absolute value of the measure mu is still a permutant measure, and the set of permutant measures is closed under linear combination. So this set has a natural structure of real vector space. So there is a lot of structure in the set of permutant measures. And you can use this structure. We stress that when the group G, this is quite important. When the group G becomes larger and larger, the lattice of permutant measures becomes smaller and smaller. So when you have a difficult group, not a trivial group, a simple group, a small group, but a big group, using permutant measures is a good idea. In other words, the theory of permutant measures becomes more and more useful to produce Geneos as the groups get bigger and bigger. Okay. Since you have more condition, when you have, if I ask you, okay, I add permutations, the conditions becomes stronger and stronger. And so you have a smaller set of permutant measures. Duality is the key point. Something difficult becomes simpler. Duality is the key point. This kind of behavior. So the previous method for building Geneos can be generalized by replacing the arithmetic mean with another symmetric function. What is the base of the idea, the main idea in the definition of Geneo that you can find here? Okay, what is this? This is an average. Since we have some weights, mu of h, and the total mass is less than 1. If the total mass is 1, you can normalize this, and you can assume that the total mass is 1, by normalization. This is just a convex combination. Okay, you are considering in practice a sum and you divide by the mass. Okay, so in this case, you are considering a symmetric function that is the average. The average is a symmetric function. You can permute the elements and you get the same result. So the idea is this. What happens if I use another symmetric function instead in the place of average? Okay. We can indeed show that when a symmetric function and the permutant for the equivalence group G are available, we can easily build a nonlinear Geneo with respect to G. This is quite important since this method here produces linear Geneos. They are linear map. But in many cases, we are interested in having nonlinear maps. So, okay, but if we use a symmetric function in the place of an average, we can get nonlinear Geneos with respect to the same group G. But in order to explain this, I need to recall the concept of permutant, which is related to the one of permutant measure. Definition, we say that a subset H of a set of every possible permutation of X is a permutant for G if either H is empty or the conjugacy action take H to H for every element of our group. Note that a subset H of a set of bijections is a permutant for G if and only if H is a union of orbits for the conjugation action of G on the set of permutations. Now I'm going to say something that is well known, but it's of use in order to understand what I'm going to say. What is a symmetric function? Let C be a symmetric subset of Rn. It is a subset C such that when you apply to C the permutation, you permute the elements of each n tuple, you get the same set C. And this happens for any permutation pi of the coordinates. A function f from the symmetric subset to R is said to be symmetric on C if its value is the same no matter the order of its arguments. That is, this equality holds for every A1 AN and every permutation pi of a set 1n. Okay, this is a symmetric function. A simple observation is illustrated here. Proposition. Let f be a continuous real-valued symmetric function defined on a compact symmetric subset of Rn. Let us call this compact subset K. Then f is the restriction of a continuous real-valued symmetric function f bar defined on Rn. Let me explain this with different words. That means this, the concept of continuous real-valued symmetric function defined on a compact symmetric subset K of Rn coincides with the concept of restriction to K of a continuous real-valued symmetric function defined on Rn. It's the same concept, expressed with different words. Okay, now let's go back to building Geneos by using symmetric functions. Let S be a symmetric function from Rn to R. Let us assume that we have a non-empty permutant H made of H1, H2, Hn for the group G. Then we can define an operator SH from the set of admissible signals phi to the set of bounded functions from X to R by setting for any admissible function SH of phi is equal to S of phi composed H1, phi composed Hn, where S is defined in the obvious trivial way. In practice, think about the average. We have phi composed H1, phi composed Hn. In the previous theorem, we said, okay, compute the average. This is the meaning of considering the sum with the permutant measure, with the weights given by mu of H. Now you say, no, we are not using the average, we are using another symmetric function. Proposition, if S is a symmetric function, G is a subgroup of a set of phi preserving bijections of X, and H is a non-empty permutant for G, then SH is a group equivalent operator, a geo, from phi G to RXBG with respect to the identity homomorphism from G to G. If the restriction of S to the this set is non-expansive, then SH is a genio from the two perception pairs with respect to the identity. So we have a way, we have a method to build geos and Geneos by using our symmetric function. But we need that the restriction of S to this set is non-expansive. If not, we have just a geo. So let me recall some basic facts about the approximation of symmetric functions by symmetric polynomials. For sure, you know about this, but anyway. In the sequel, we will denote the symmetric group over the set 1n as Sn. Let K be a compact metric space, and C of K be the vector space of continuous real-valued functions on K. With a slight abuse of notation, in the following, we will confuse each polynomial with a function it represents, restricted to the domain we are considering. Furthermore, if I is a finite subset of n power 2n, we will say that a polynomial of this kind is a symmetric polynomial if the permutation belonging to Sn, that is any possible permutation, take I to I, and the coefficients of a polynomial are related to each one by this equality. This is just the definition that you already know, and anyway, it's quite natural. You permute, you exchange the variable, and you get the same polynomial. So the coefficient, when you permute the variables, must be the same, okay? A symmetric polynomial. In the next two slides, we will show that any symmetric function can be approximated with arbitrary precision by symmetric polynomial. This is not, of course, this is not research. This is a theory. I'm just recalling something well known, okay? So a subset A of C of K, functions from K to R, is an algebra if it is a vector subspace of C of K that is closed under multiplication. That is, if F and J belong to A, then the product of F and G belongs to A too. Given a set S of functions on K, we say that S separates points if for each pair of points ST belonging to K, there is a function F that is able to see the difference that is such that F of S is different from F of T. Given a set F of functions on K, we say that S vanishes at the point S if F of S is equal to 0 for any F belonging to S. Then we have the well-known Stone-Weierstrass theorem. An algebra A of continuous real-valued functions on a compact metric space K that separates points and does not vanish at any point is dense in the set of continuous functions from K to R with respect to the max norm referred to the domain K. And if we use this theorem, and we can indeed use it in this context, we have this corollary. Let K be a compact subset of Rn. The algebra of all polynomials, P of y1, yn in n variables, is dense in C of K with respect to the max norm referred to the domain K. Okay? So, is dense, so we can get this proposition. Let K be a compact and symmetric subset of Rn. If this function from K to R is the restriction to K of a continuous symmetric function, S from Rn to R, and we consider the max norm referred to the domain K, pay attention, not the general max norm. We are computing just the max norm restricted to K, then for every positive epsilon, there exists a symmetric polynomial Q in n variables such that the distance between the function S restricted to K and the restriction of our polynomial, our symmetric polynomial to K, the max norm distance between these two functions is less than or equal to the value epsilon. What is the meaning of this list of words? The meaning is that we can restrict our attention to symmetric polynomials. We have symmetric functions, but we can approximate them by symmetric polynomials. So, up to some error, we can forget about considering any possible symmetric function, and we can say we will focus just on some particular symmetric functions, the symmetric polynomial, since each symmetric function can be well approximated by symmetric polynomials. Okay, this is a message. Now, think about symmetric polynomials. You know that the elementary symmetric polynomial in the elementary symmetric polynomials in the n variables a1, an are defined this way. Sigma 1 is just the sum a1 plus a2 plus an. Sigma 2 is a1 times a2 plus a1 times a3 and so on. You consider any possible product of your variables and you take the sum and so on, taking the product of 3 or 4 and so on until you get the product of any variable a1 an. These are the elementary symmetric polynomials. Okay. When we consider the Geneos produced by the average, we were considering sigma 1 by dividing by the weights expressed by the mass, okay, by the measure. Now we can consider also the other elementary symmetric polynomials. In order to do that, we have to use the fundamental theorem on symmetric polynomials. Any symmetric polynomial in n variables a1, an is representable in a unique way as a polynomial in the elementary symmetric polynomials sigma 1, sigma n. So it's the same. Instead of considering any possible symmetric polynomial, you can consider any possible polynomial in the elementary symmetric polynomial sigma 1, sigma n. Now, in conclusion, what I'm saying is this. If an equivalence group G is chosen and the G of, what I'm saying is that I'm speaking about this result, okay? This is a way to get Geneos. Use a symmetric polynomial, a symmetric function, but instead of a symmetric function, you can use an approximation. It is a symmetric polynomial, but a symmetric polynomial is a symmetric, as I have shown previously here, is just a polynomial in the elementary symmetric polynomials sigma 1, sigma n. So, in conclusion, if an equivalence group G is chosen and the geo f equal to sh is built, we can approximate f in the following way, provided that x and phi are compact. First of all, we can approximate the continuous symmetric function S by a polynomial P from Rn to R. We can do that. with an arbitrarily small error epsilon on the symmetric set given by the image of phi to the nth power, which is guaranteed to be compact. Then we can consider the symmetric polynomial Q that is obtained by averaging the previous polynomial, considering any possible permutation of A1, AN. Finally, we can consider the geo f prime defined by setting f prime of phi equal to Q of phi composed H1, phi composed Hn. We can easily see that the distance between f and f prime is as small as you wish. Okay, if your approximation of a polynomial is good, you get another genio by using the same theorem that approximates the original genio associated with the original symmetric function S. Okay, so the fundamental theorem of symmetric polynomials guarantees that the restriction of to this set of any continuous symmetric functions can be approximated arbitrarily well by the restriction to the same set of a polynomial in the elementary symmetric functions, defined in this way. Instead of considering any possible symmetric polynomial, I used any possible polynomial in the elementary symmetric functions. And now, what we can say is that we already know that the associated operator associated to these symmetric functions is a group equivalent operator. Unfortunately, since this operator is not guaranteed to be non-expansive, we cannot say that this is a genio. Maybe it is expansive on our set of admissible data on Rn, and so we cannot say that we have a genio. What we can do is considering, this is just technical, some constants that we can define on the basis of a knowledge of our data, okay? And please focus on the last one, C, that is defined on the basis of the other constant, okay? So you make some computation, there is a recipe, and you get a constant, okay? Now, SH was not a genio, but SH divided by C is a genio. So C takes care of a non-expansivity and reduces a geo to a genio. This is just technical. It is not important from the general point of view. Okay, it is true. You get just a geo, but you can transform it into a genio by normalizing this by a suitable constant. And this is the guy. This is the normalization of a geo in order to get a genio. Okay, let me just read the theorem and skip the technical steps. Let us assume that G is a subgroup of a group of phi preserving bijection, and H is a non-empty permutant for G. If S tilde is a polynomial in the n elementary symmetric functions, then this operator, SH hat, is a genio from phi G to this perception pair with respect to the identity homomorphism. So, do you have a permutant measure? Then you have a way to get a genio. Okay, this is the summary of a game. Now, until now, I have just said there are procedures, methods to produce genios. We have some machines, you put inside some information and you get genius. You can populate your world of genius. And you have, for example, by considering the convex combination, a way to transform a finite set of genius into an infinite set of genius, where you can look for the best genio, that is the best observer that can approximate your real observer. Now, this is a quite recent paper published on the Annals of Mathematics and Artificial Intelligence on the finite representation of linear group equivalent operators via permutant measures. What is the main theorem? I'm going to read it. Let us assume that G is a subgroup of a group of permutations of X, transitively X of the finite set X. This assumption is quite common, quite frequent in modern theory of neural networks. You need transitivity of the action. Transitivity just means that your group is able to take each point to any other point. Think about the group of translations. I take this point, I would like to take this point to this point. Is there a translation able to do that? Yes, there is. So this action is transitive. Okay. In this case, there is just one translation to do that. But if I take the group of isometries, there is plenty of isometries able to move this point to this. For example, I could translate and then I could rotate, letting this point fixed. Okay. The action is transitive. Of course, if I take the trivial group is not transitive. There is no way of moving this to this. If I just take the translation in this direction, this group is not transitive. I cannot take this point to this point. Is that clear to you? So let us assume that the action of G is transitive of the finite set X, and that F is a map from a set of real valued functions defined on X to the same set. Pay attention, the map F is a linear genome from Rx to Rx with respect to identical homomorphism if and only if a permutant measure mu with respect to G exists such that our map F is this convex combination for every function, for every admissible signal, and the total mass is less than 1. What is the new information? You have seen one implication of this result. I've told you that if you have if you take this kind of summation, you get a linear genome. But now this theorem guarantees that any genome, any linear genome, can be obtained this way. Maybe you have heard about a way of obtaining any possible equivariant operator. There is a famous result that says that any operator that is equivariant in the case of transitive action can be obtained as an integral over the group. You can average over the group. What is the problem? The problem is that you have to integrate on a huge group. Think about the group of any possible isometries of Rn. For any isometry of Rn, you have to take a summand and you make this computation. In practice, you cannot do it. But now we have a different way. We are considering permutant measures. And please remember about the example I have done about the cube. The group is pretty large. We have, not in this case, it is not large, but the number of elements is 24 elements in the group. The permutant contains 3 elements. So the method based on the integration of the group requires to compute a sum over 24 summands. This method requires to sum 3 summands. This is the difference. Okay. Obviously, this is just a trivial example. Think about the integrating of the group of any possible projectivity, for example, or something like this. In simple cases, you can see that, okay, I'll skip this. But you can have that the permutant contains just 2 elements and you have a group with a huge number of elements. Okay. Let me see if I can tell you something about, okay, there is half an hour. I'd like to give you the flavor of a proof in order to see what is inside the proof. Okay, I'll skip the direction that you have already seen, the direction that says, okay, you have a permuted measure, you can get a Geneo. We know about that. Now we have to prove that if I give you a Geneo, you can look at this as a Geneo produced by this method. Okay, so let F be a linear Geneo from Rx to Rx with respect to the identical homomorphism. The proof of this direction of the representation theorem for linear Geneos is based on the matrix B, Bij, associated with F with respect to the basis 1x1, 1xn of a vector space Rn. Okay? So we take this basis and we take the matrix describing our operator, our linear operator, with respect to this basis. Now we consider the positive part and the negative part of this Geneo, F plus and F minus, defined by these equalities. And we also consider the matrices associated with F plus and F minus with respect to the same basis we have previously considered. So we have B plus and B minus. And these matrices are non-negative matrices, since I have separated the two parts, the positive and negative parts, changing the sign to the negative part. Now, since the action of G on X is transitive, we can prove that an n-tuple of real numbers alpha, alpha 1, alpha n, exists such that each row and each column of delta plus, B plus, can be obtained by permuting alpha. And the same holds for B minus. Now, to proceed, we need the following well-known lemma, the Birkhoff-von Neumann decomposition. Let us assume that we have an n times n real matrix M with non-negative entries, such that when you compute the sum of elements of each row, you get C bar. And when you compute the sum of the element of each column, you get the same total, the same value C bar. So you have a matrix, you compute the sum for each row, you get C bar. You compute the sum for each column, you get C bar. We say that this matrix is doubly stochastic. Okay, we have a doubly stochastic matrix. The classical Birkhoff-von Neumann decomposition guarantees that for every permutation of X, a non-negative real values C of H exists such that the sum of these values is C bar, and M can be represented as a linear combination of a permutation matrices associated to this permutation H. You know that each permutation H has an associated matrix, okay, that describe the permutation with respect to the basis that I have taken previously. So M is just a linear combination of permutation matrices, and the coefficients are C of H, varying H in the set of bijections of H. This is a consequence of the Hall's marriage theorem. Maybe you know about that, I do not know, but anyway, it is a well-known result, okay? So, Hall's marriage, teorema del matrimonio, Hall's marriage theorem. This result follows. For every bijection H, two non-negative real numbers, C plus of H, C minus of H, exist such that the positive part of F, F plus, is equal to this linear combination, and the negative part is equal to this linear combination for every function. Moreover, the matrices associated with F plus and F minus commute with the matrices describing the permutation, pay attention, not H, but in the group. This is just a way of rephrasing the fact that the operator is equivariant. And now I'm going to the end. Okay, I'm skipping the details. There are plenty of details here, but I'm just illustrating the line. Now, for each H, for each bijection H, let us consider the orbit of H under the conjugation action of G and set, remember, we have to define a permutant measure. And we have to prove that with respect to that permutant measure, when we apply our recipe, we get our Geneo. Okay, so I have to define a permutant measure. And I define the positive part of the permutant measure, mu plus, that is defined this way, and the negative part that is defined in a quite similar way. In other words, we define the measures mu plus and mu minus of H, of each permutation H, as the averages of the functions C plus and C minus along the orbit of H under the conjugation action of G. After that, we can compute the difference between the positive part of the measure and the negative part of the measure, and we get a permutant measure, the permutant measure that we need to prove the statement of a presentation theorem for linear Geneos. There are computations hidden here, but anyway, if you use this measure, it works. And now you can prove that the Geneo that you have given me, asking for a representation, can be represented this way by using our permutant measure. And we can also prove that the total mass I have defined is less than 1. So we have a representation theorem. Let me repeat, each linear Geneo with respect to the transitive action can be represented in that way by using a permutant measure. And in some cases, this is better than representing this Geneo as an integral on the huge group you have, since the support of the permutant measure can be quite small. Now I'm going to end, and the last section of my talk concerns the use of Geneos in applications. So maybe it is not clear. This should be yellow. It is a cube. It is just a die. Okay. And in the first example is not a real example. It is not a real application. The other example will be a real application, looking for pockets in proteins. This is just an example to illustrate the use of Geneos. Imagine that we have real dies. Okay, you know that in a real die, the sum of the opposite phase is 7. Okay, in each real die, the sum of these two phases is 7. This two phase is 7. The sum of these two phases is 7. This is a real die. This is not. 4 and 3 are not opposed. I asked one of my collaborators to produce 10,000 dice, random. I mean, what is a die in this representation? We have to color the faces, and you can change the level of gray of the spots. And so the face is not just 4 points, it is an image. Okay? And you have 6 images, and you can produce randomly these 6 faces, and you get 10,000 dice. Okay? You do this for real dice and for fake dice that do not exist in the market. Okay? What happens when we apply Geneos? Let me read this. We produce 10,000 dice, a training set of size 7,000, and a test set of size 3,000. Then we applied the principal component analysis to reduce the test set and the test set transformed by a suitable Geneo optimized of the training set. So in plain words, think about the die. There is a lot of pixels in each image. So we have a lot of information. It is an image. But we reduce this information to two numbers. We use principal component analysis. So we have some thousands of points. We reduce this information to two real numbers, okay, by using principal component analysis. So now each die is a point in the real plane, two numbers. Each die is a blue point or an orange point. Blue points are real dice. Orange points are fake dice. You can see that when you do not apply Geneos, this is the distribution of information. These dice were produced randomly. Okay, there is some geometry here since it is a cube. There is a group. The group is the group of isometries taking the cube to the cube. Okay, so 24 transformations. Okay, and you can see that information is not clearly separated. But now we say, let us take a Geneo based on permutant measures. And exactly, we take three families of free permutant measures. Okay, it is the permutant measure that you have seen in the example of the cube. You remember the three planes, okay, H1, H2, H3. Okay, we have a permutant measure in that case. And we optimize, we take three permutant measures, and we took the Geneo produced by the first permutant measure, the Geneo produced by the second permutant measure, and the Geneo produced by the third permutant measure. So we have a triangle, three vertices, and we take any possible Geneo that we can obtain by convex combination. Is that clear to you? We have three permutant measures. You have seen one of them in my example. And for each permutant measure, we have a Geneo. So we have three Geneos. Now we can take the whole triangle, each point, each convex combination of a three permutant measure. And we optimized the Geneo in order to separate the information. Now we have this Geneo, and this is the expert. Now, in order to ask, for example, a simple neural network to discriminate, to recognize fake dice and real dice, we say, don't work on the information. Work on the information where we have applied Geneos. And you can see that it's quite easier to separate the information. Geneos are kind of observers that forget about useless information and do that by looking at the group. Maybe this is the most important information I can give you in my talk. Geneos are kind of observers that are able to forget about useless information. This is quite important. Now a paper that is available on the archive, GeneoNet, a new machine learning paradigm based on group equivalent and expansive operators, an application to protein pocket detection. This is not a trivial example. This is real research that we are doing together with Dompe Farmaceutici. They are interested in pockets in proteins in order to link ligands with protein for creating forbidding drugs. Okay. So what is our purpose? You can see here on the left the protein 2QWE, and they are pockets. You can see them colored. They are just cavities where you can plug drugs, ligands, okay? And at Dompe are interested in finding good locations where they can insert drugs, okay, ligands. So the problem is, how could we obtain the correct location of pockets? Okay, the idea is using Geneos in order to locate this. For sure, we know that it is not important the position of the protein. We can rotate the protein, we can apply the transformation in the group of isometries, and our answer should change in the same way. When we rotate the protein, if I say that here I have a pocket, when I rotate the protein, I should say that in the corresponding location, I have still a pocket. So we are considering the group G, the equivariance group, given by isometries, the isometries of R3. Now, what happens? We considered 8 different channels. What is a channel? It is a representation of information with respect to different point of view. We have a protein. What is a protein? It is a distribution of atoms. This is true. So we need the functions that describes the density of atoms in R3. Okay? I have an atom here, this is empty, and so on. So it is a function from R3 to R, describing the position of the protein. But we have also an electric field, the electric field of a protein. And this is another function from, if we consider the intensity, from R3 to R. And then there is the lipophilic properties, the ability of having a link with fats, how do you say in English, with our protein, okay? So there is a list of 8 different channels, different properties of the information we are interested in studying, our protein. So we take these 8 channels and we feed these 8 channels to Geneos. And then we combine this information in order to have a function that says, okay, I think this shallow network of Geneos think that here I have a pocket, here I have a pocket, here I have a pocket, and so on. In this zoomed version of the same image, you can see that there are numbers inside the cavities. The numbers are the score of each pocket. When you have an high number, it means that the probability that there is a real pocket there is higher. Okay, and there is symmetry since this protein is symmetrical. So if you find a pocket here, you have to find another pocket in the corresponding location. What is the advantage of using Geneos? We have compared the results obtained by GeneoNet, which is a shallow network of Geneos, with some other state-of-the-art methods to locate pockets. You can see P2Rank, deep pocket, caviar, sitemap, F pocket, cavis. And what happens is this. The higher, the better. Okay? The blue line is the result given by GeneoNet. The other results are given by the other method. But what is the important point? The important point, for example, is that GeneoNet uses 17 parameters. The deep pocket, that is convolutional neural networks, requires more than 500,000 parameters. So it is advantageous from the speed, from the point of view of speed. And when you work with proteins, you have 1 million possibilities. You'd like to exclude some protein that does not that do not work in some sense, or ligand that do not work with that protein. And this is a big advantage. In practice, when you use Geneos, you are saying, okay, I know something about the geometry of the problem. It is not true that I do not know anything. I know something. For example, in the case of protein, I know that a pocket should be, in some sense, a cavity. I know that. Why should I teach a neural network that a cavity is something similar, a pocket is something similar to a cavity? I know that. So I just move in the space of observers that know this important information. I do not exit from the space of good observers. This is quite an important point. This is the reason we can reduce the number of parameters. When you take a neural network and you say, okay, the convolution is represented by these metrics, the weights are in the metrics, and you change the weights by using a gradient descent, in general, you are exiting the space of good Geneos. You are saying, I do not know anything. I change this just with respect to the gradient. But if you know that a pocket is in some sense a cavity, from the point of view of electric field, you have some kind of property and so on, and you can insert this information, and this kind of knowledge engineering, then you obtain some GeneoNet or something like this. It is quite faster in giving an answer, and most of all in learning. So, what is the main point in this approach? What is the perspective of people working on Geneos? We are looking for a good compositional theory. Compositional means rules to combine Geneos. Think about Lego. It is a game. You have to build something. You need smart pieces to join together. Okay? We are looking for a good compositional theory for building efficient and transparent networks of Geneos. Some preliminary experiments, we have some other experiments with different kind of data, electric power towers. Okay, forget about this. Some preliminary experiments suggest that replacing neurons with Geneos could make deep learning more transparent and interpretable and speed up the learning process. So the idea is that we are here, many neurons, we'd like to get here, just a few Geneos, but you need to have knowledge. If you do not have any knowledge, it is a bad idea to use Geneos. Discard them. But if you have some knowledge, and in most of the cases you have some knowledge, if you can insert by using Geneos, you can speed up the process and get better results. So that's it. I get that it's better if I stop here. 8 minutes. I do not know. Yeah. Any questions? I should maybe I should have a look. Okay, where? No. Stop recording. No. Ok, here. È meglio se lo fai te che io. Non succede niente.